Okay, what is the equivalent resistance between points A and B? So I'll just draw the figure here. So we've got A, my resistances probably need a bit of work, but that's fine. Pretty sure it's somewhat obvious what these are. Okay, so what's the equivalent resistance between A and B? We're given that this is 3.70 ohms, 2.20 ohms, 2.00, 5.10, 4.40, 6.20. Okay, so we're going to need to use just two equations here. So if we have resistances in series, then our total resistance is just the sum of the resistors. Whereas if we have resistances in parallel, then 1 over the resistance, the total resistance, is the sum of 1 over those resistances. So now just to apply this, so we've got some resistances in parallel, or some resistors in parallel and some resistors in series here. And we're going to need to apply these in different orders. So if we look here, these are all in series, and they're in parallel with this guy, and then that segment's in series. So first, let's start off by that. So the total resistance there is just because it's in series, the sum, so 2.20 plus 2.00 plus 4.40, and that comes out to be 8.60 ohms. And so we can redraw the figure as something like this. So we've got, and so we've collapsed those 3 resistors into 1, and so we've got this 5.10 ohms, and then this 8.60 ohms, 3.70, and 6.20. And now this segment is in parallel. So 1 over the resistance here is 1 over 5.10 plus 1 over 8.60, which is equal to 0.312, or the resistance is 3.20. And so now we have another equivalent circuit we can draw, where now we have A, I'll into something. Okay, 3.70, 6.20, and 3.20. And now we just have 3 resistors in series, so our R is just 3.70 plus 3.20 plus 6.20, which comes out to be 13.1 ohms. 10, I guess, in retrospect. There we go. So 13.10 ohms. So there's our total resistance between points A and B. So treat the first segment as series, then parallel, then series, and we get 13.10. So that looks good.